I can do this weekend, get back as much as I can. Okay, so last time we talked about this setup. Let's imagine, so this is from last time. We're talking about this Atwood machine. And last time we did this calculation where I didn't talk about it as being in an elevator before, but let's imagine that it's in an elevator at rest, okay? And we had, I don't remember which side the big one was on, but we had a, was it a 100 or a 10 and a 5? Okay. And this is an elevator. And let's say that the motion of this stuff is being observed by a video camera. I don't really know what a video camera looks like. Okay. If the elevator has no acceleration, the acceleration of the 10 kilogram mass, we calculated this last time, was negative 3.27, I think. Is that right? So now we want to know what's the acceleration of the 10 kilogram mass. Thanks. If the elevator's acceleration, or if the elevator accelerates up at, and I think I said 2 meters per second squared. Well, if that elevator is accelerating up, then this camera is accelerating up too, with that, that same amount. So your first glance, your first thought would probably be that the camera is going to measure the same acceleration that it did before. The problem is the reason that doesn't happen is that if you think of this camera as a coordinate system, before the elevator accelerates, it's a perfectly good Newtonian inertial coordinate system, right? Because the origin isn't accelerating. Once this elevator starts accelerating, the calculations change because this is not an inertial coordinate system. So we can't base Newton's laws on the acceleration that it measures, okay? And so we're going to have to take that into account. And what we'll see is that the downward acceleration of the 10 kilogram mass when the elevator's accelerating up is bigger. It's like you're adding to the gravitational field. Okay, so the main idea is that we can't use Newton's second law based on the acceleration measured by the camera. And using the notation of relative motion, and acceleration is what we would call the acceleration of the mass relative to the elevator. And we can't do that because it's non-inertial. The origin is accelerating. So what we have to use is the acceleration of the mass relative to the ground. Yes, it depends on it, but it also depends on the acceleration of the elevator. So relative motion says the acceleration of the mass relative to the ground is equal to the acceleration of the mass relative to the elevator plus the acceleration of the elevator relative to the ground. This is the one that is given in the problem to be 0, positive 2 meters per second squared. Okay, so let's draw a free body diagram of the 5 kilogram mass. There's a cable tension up and a weight force down of 49.05. That weight doesn't change due to the acceleration. The acceleration of the 5 relative to the ground is equal to the acceleration of the 5 relative to the elevator plus the acceleration of the elevator relative to the ground. And I'm going to write that as 0 A5. So what I'm talking about, A5, is relative. Maybe I should put that relative thing in. Okay, so 5 relative to the elevator plus 0.2. And we can write that as 0 A5 relative to the elevator plus 2 in the z component. Everyone with me on this so far? And now Newton's second law says 0t plus 0, negative 49.05 is equal to the mass times the acceleration relative to the ground, our only inertial reference frame, 0 A5 relative to elevator plus 2. That gives us the first useful equation that says t minus 5a 5 relative to e is equal to 59.05. That's one equation with 2 variables, so we can't solve it yet, but we'll set it aside and use it when we get a system that's big enough. Okay, when we get a system where we have enough equations for the number of variables. And now we'll isolate the 10 kilogram box. There's a weight, this time it's 98.1. It's the same cable, so we still have the cable tension T up. the acceleration of the 10 relative to the ground is equal to the acceleration of the 10 relative to the elevator plus the acceleration of the elevator relative to the ground. And so that's going to be 0 A10E plus 0, 2. So that's 0, and then in the y component, A10E plus 2. And then Newton's second law says 0t plus 0, negative 98.1 is equal to 10 times the quantity, or times the vector 0, A10 relative to the elevator plus 2. And we get our second equation. It says t minus 10 A10 relative to the elevator is equal to 10, what's that equal to? Add 20, so 118.1. Okay, so now we have a system of two equations. Can we solve this system? No, because this is a third variable. So we have two equations, three variables. That means we need one constraint equation. Where's that constraint equation going to come from? It comes from the same place that it did before the elevator was accelerating. Do you remember what that was? Yeah, the rope stays the same. So inside the elevator, according to this camera, what this camera sees is that when this goes down an inch, this goes up an inch. And so there's an equal and opposite relationship between displacements and velocities and accelerations. And so that relative acceleration A5E is equal to negative A10E. Notice that constraint equation doesn't hold for the acceleration relative to the ground. You know, if that elevator was going up at 1,000 meters per second squared, both of them would be accelerating upwards at close to 1,000 meters per second squared. But inside the elevator, that does hold. Okay. Any questions about that constraint equation or any of this yet? Yeah. No, they have to be linearly independent equations. So those reduce down to the same equation, and so it wouldn't help you. Yeah, and so that's why also sometimes, this is equation 3, sometimes it can look like you have enough equations to solve a system, and then when you try to plug in the matrix and use reduced row echelon form to solve it, there's no solution, and that's because one of those equations, it turns out, is just a linear multiple of other equations that you have. So they have to be linearly independent. Okay, so now we have this system that says, if we make this substitution, our first equation says t plus 5A10 relative to the elevator is equal to 118.1, I believe. And our second equation says t minus 10 a 10 relative to e. Oh no, the first one I did that constant wrong. What was the constant on the first one? 59.05. The second equation is 118.1. And I'll subtract these two equations. The t's cancel, and you get 15 acceleration of 10 relative to e is equal to, what can someone add those for me? Oh no, subtract them. So you get negative 59.05. And so I believe what you get is acceleration of 10 relative to e is equal to negative 3.94 or so. Is that right? So the acceleration of the 10 kilogram mass observed in the elevator is equal to 0, negative 3.94 meters per second squared. The first one was negative 3.27. So the fact that the elevator was accelerating upwards had the effect of increasing the acceleration of this system, like increasing the gravitational field. You could do it if what you wanted was the acceleration relative to the ground. But what we were trying to compare is what this camera was seeing in the two cases. And so what we calculated there was the acceleration measured by a camera that's accelerating with the elevator. That's the acceleration of the mass relative to the elevator. Okay, so those are the two we're comparing. I guess my question is why did we need the We needed the relative motion equation because we had to represent the acceleration in an inertial coordinate system. And the acceleration of the mass relative to the elevator is not an inertial acceleration, okay? Because that coordinate system is accelerating. So we had to use relative motion to get an acceleration in an inertial coordinate system that we could use in Newton's laws. Okay? Yeah. Yeah, I made the substitution here. So t minus 5 times the acceleration of 5 relative to the elevator. And that's the one that I substituted in this constraint equation. Any other questions? It's pretty cool, isn't it? Like you get to see the effect that, because what would you get if you use Newton's second law based on that non-inertial acceleration? Well, then you would just do the same problem over again that we did when there was no acceleration. And that shows you how wrong that answer would be. That's the effect in this case of using a non-inertial coordinate system in Newton's law. Any other questions? Okay, let's do one more example with these constraint equations. I think the problems that you have to do, eventually you're going to have to do one of these Atwood machines with a more complicated pulley system. So I'm going to do a problem with a more complicated pulley system where it's not accelerating. And then you'll just have to go through the steps of the relative motion and everything when the system is accelerating. Okay, so let's say we have this example There's a pulley hanging from the ceiling there. And we have this system of hanging pulleys. It's a little hard to draw. Okay. And there's a mass attached to these hanging pulleys. Let's say that that's 10 kilograms. And do you notice any problem with the setup yet so far? Can anyone estimate what the acceleration of the 10 kilogram mass would be right now? Yeah, very good. Down at 9.81. So let's add a cable. And the other side of this cable is attached to a 5 kilogram mass. Yes, those are all vertical. Is that what I want to do? I guess that is what I want to do. Okay. What's the acceleration? Of the 10 kilogram. Okay, well, a free body diagram. I'll start with the 5 kilogram mass. We have 49.05 down and an unknown tension T up. And so Newton's second law says 0T plus 0, negative 49.05 is equal to 5 times 0, A5. And so our first useful equation says T minus 5A5 is equal to 49.05. And then a free body diagram of, let's say, all the other hanging stuff. So that means I'm going to isolate these two hanging pulleys, this structure here, and then the mass. We're neglecting the weight of everything except that mass. So we have something like this. The weight is 10 times 9.81, so 98.1. And now where does the outside world make contact with this system? Nowhere around the mass, nowhere here. So when you get up to this side of the pulley, there's a cable, right? When you get to the other side of the pulley, there's a cable, another one there, and another one there. And all of those are pulling away from the chosen body, parallel to the cable. And it's all the same cable, so it all has that tension T. So we have T, 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 T. Any questions about that? If you have trouble visualizing that, I think I mentioned you can imagine isolating just a little stump of the cable at every place that it contacts, and then that tension just acts right out of that stump of cable. And so you can see it has to work like that. And so Newton's second law says 0t plus 0t plus 0t plus 0t plus the weight. 0, negative 98.1 is equal to the mass times the acceleration of the 10 kilogram. And so our second useful equation says 4t minus 10a10 is equal to 98.1. Can we solve that system? No. We have 3 variables, 2 equations, so we need one constraint equation. And what's that constraint equation? Right. So I'll write it as the acceleration of 5 is the negative acceleration of 10. Oh, yes. No, I glossed over something important. You're exactly right. Okay, so we have to think through this again. Okay. Geometry on this one is trickier. Okay, so let's think about this for a second. So if you pull the 5 kilogram down 1 inch, how far up does the 10 kilogram move? A quarter inch, yeah. You can think of it this way. If you're going to get an extra inch from the cable below this contact point here, okay, that's going to come, all of that 1 inch is going to come from somewhere in all of this stuff. And if this thing is going to stay level, it's going to have to take a quarter of an inch from here, quarter from here, quarter from here, quarter from there, which means if this goes down 1 inch, this only goes up a quarter inch. So A5 is negative 4 A10. You know, if A5 is if the displacement of the 5 kilogram is negative 1, then the displacement of the 10 is positive 1/4. So that relationship is that A5 is equal to negative 4 A10. Who's with me? Okay. That's equation 3. And so I'll make that substitution into the first one. So T plus 20 A10 is equal to 98.1. No, that was the other one, wasn't it? 49.05. And the second equation says 4T minus 10A10 is equal to 98.1. So I guess I'll do 4 times this equation minus this equation. And we get 0T, 70A10 is equal to, 4, or 90, right? 4 times 20 is equal to negative 49.05. And so what do you get for A10? What is it? 1.09 meters per second squared. Okay, this is negative. Oh, yeah, I did. You're right. Thank you. So 4 times this, yeah, right. So negative 98 point, no, positive 98.1. And then you get what you told me, right? A10 is equal to 1.09. Okay, let me think about this. Meters per second squared. So A10, the acceleration is equal to 0, 1.09 meters per second squared. Okay, I was expecting this to balance. So what's going on here? Oh, no, right, it won't balance because I have so many pulleys. Okay, so what we got here was pulley advantage, setting up this system of pulleys like a block and tackle meant that even though the 5 kilogram mass is half of this 10 kilogram mass, it's more than enough to balance this weight. And so the upward acceleration of this is 1.09 meters per second squared. And what would be the acceleration of the 5 kilogram mass? That's right, downward at 4.36. Yep. Yeah, if I would have, so here's why I was confused. I was imagining it like this. So if we had one pulley there, one hanging pulley, and then set up the system the same way like this. then you would see that those are perfectly balanced. Nothing would accelerate. It's because I put in another 2 pulleys that we had in acceleration, which is good because it's more interesting. I was sort of thinking this was going to be a boring problem, but any other questions about that? So this would give no acceleration. Try it if you feel like it. Okay, so that's all I'm going to say about particle kinetics. So now we're going on to really what we're going to spend almost the whole time on is rigid body kinetics. So we're on to rigid body kinetics in 2D. And I mentioned last class, and I'll mention it again a couple times, that particle kinetics in 2D and 3D is qualitatively the same thing. Nothing really fundamentally changes. Rigid body kinetics in 2D and 3D changes a lot, and I'll point out where that change comes from when we get there. But we're going to be talking about approaches that work in 2D. You have to do some more complicated stuff in 3D. We're still assuming non-rotating coordinate system. Okay, so I'm going to start by just talking about what we know for general collections of particles. And so here we'd be talking about a bag of marbles, a glob of pudding, we're going to break all of this up into a translational equation of motion and a rotational equation of motion. So get up into translational and rotational motion. For translational motion, we can actually make a very strong statement, a surprisingly strong statement. There's a very strong, useful result. Newton's second law says take all the net forces, all the external forces, and that's equal to the mass of the general collection times the acceleration of the center of mass of the general collection. So this is true for any collection of objects. So think about like, so I don't know, I haven't tried to jump in a long time, but I'm going to just pretend I'm jumping. Okay, so if I do this while I'm in the air, what's the acceleration of my center of mass? Yeah, I'm in free fall, it's negative 9.81. But what if I do something funky with my limbs? You know, that's going to cause all these internal loads. I'm going to lift something up that, you know, so what was the acceleration of my center of mass there? Still negative 9.81, which is a surprising thing, right? But this result says that no matter what that collection of particles that makes up my body does, you can calculate the acceleration of the center of mass by just figuring out the total forces applied externally. It seems sort of wacky, right? I mean, if you have 1,000 marbles in space and you get them all moving and they crash into each other and do all this stuff, what's going to be the acceleration of the center of mass? After you let go of them, it's going to be 0. You know, it's so anyways, that's a strong statement and a stronger statement than you might expect to be able to make without knowing anything about the type of object. For rotational motion, we're not so lucky. No such luck. It would involve, there is some stuff you can say, but it would involve calculating the angular momentum of each individual particle and adding them up. Well, it really would be the calculating the change in angular momentum. I'm not even giving you an equation though, so and that's a lot more, a lot less meaningful description of the motion than just talking about the acceleration of the center of mass, right? There's a lot of particles that make up like my body, for example, and you don't want to sit there trying to calculate the change in angular momentum for each one. But if the particles are organized into a rigid body, you get a useful translational equation and rotational equation. So for rigid bodies, for a rigid body, Newton's second law says F net is equal to the mass of the body times the acceleration of the center of mass. And the rotational version of Newton's second law says the net moment, I'll call it the moment about A net, is equal to the time derivative of the angular momentum about A. And in 2D, well, that's true in 3D too. But in 2D, the most useful form is that add up all the moments about A. That's equal to the moment of inertia about A times the angular acceleration. And remember, for the people who've taken statics, when you use the rotational equation for statics, you can make that A anything you want. We're severely limited in dynamics with what we can choose as an about point. So this A has to be either one of two things. It has to be at the object's center of mass, or it has to be fixed in the coordinate system and the body. So an example of number 2 would be like if a body is connected to the ground by a pin joint, then as the body's rotating around that pin joint, that one point where the pin's connected is fixed on the body. The body's locked in place there, and it's also fixed in the ground where the coordinate system is resting. Okay. Every rigid body has a center of mass, so you can always use this one. Okay. Not every rigid body has a point that's fixed in the coordinate system in the center of mass. That's, that's determined by the joints and that kind of stuff. So you could always just use this one and forget about this one, except that when there is a fixed point, it makes the math a lot simpler. And so what we're going to use as an about point for rotational Newton's second law is if there's a fixed point, we're going to use this, and if there's not, we're going to use this. Okay. For rigid bodies in 3 dimensions, it turns out that this isn't a real useful formulation. We end up having to use this for reasons that I won't go into now. We might get to it later. But for all of the 2D stuff, this is the story. That's the translational equation of motion, and that's the rotational equation of motion. Yep. What was H? H is the angular momentum. Angular momentum vector. Any other questions? Okay, that's all.